Okay, thank you everybody for having us here. I'm Michael Goodman, this is Colin Hale, and we are working with our advisor, Dr. Greg Carling. And as mentioned, our project is characterizing the Great Salt Lake dust relative to other sources. And our project is funded by the Forestry, Fire, and State Lands here in Utah. All right, so this is our outline. First, we'll discuss our purpose, which is to characterize the dust emissions from the Great Salt Lake and compare them to other sources in the region. We will then talk a little bit about some background. We'll discuss general effects of dust and the Great Salt Lake dust, more specifically. We will then talk about our methods. So we will discuss our sampling area, and we will also discuss some of our lab procedures, which we are going to be working on. Finally, we will discuss expected results, because this is all still in the making. We have no results yet, but we have expected results, which we will discuss. All right, so our purpose, as mentioned earlier, is to characterize Great Salt Lake dust to other regional sources. So we will first figure out and identify dust emission sources. So we will go to different areas and try to chemically classify the dust sources, such as the Great Salt Lake and the severe lake bed. We will also try to sample and chemically distinguish the dust that is deposited along the Wasatch Front. Once we have chemically analyzed those two sources, we will try to identify where the dust being deposited is sourced from, whether it is from the Great Salt Lake area or whether the dust is coming more from the severe lake bed more to the south. So why is dust so important? First, dust contains high concentrations of heavy metals, toxins, and salts. Each of those are harmful to human health. They cause allergic reactions, bloody noses, and because the dust particles are so small, they get lodged into our lungs instead of being expelled when we breathe. And that can cause lung disease and cancer. In addition to these human health effects, dust lowers the visibility for pedestrians, drivers, and airplane pilots, which can greatly affect the economy here in the Salt Lake area. Okay, so one example of harmful dust comes from Owens Dry Lake Bed in California. So in 1913, Los Angeles began to pump water out of Owens Lake. After 13 years of pumping, the lake was completely dry, and it left this large area of dried lake bed, which produces over 25 days per year of harmful levels of dust in the atmosphere.
So the question is, does Great Salt Lake dust have the potential to become a dust emission source like the Owens Dry Lake Bed? So here from the Division of Air Quality, we took a screenshot from April 14, 2015, and they're showing high levels of hazardous air quality in the Salt Lake area because of a dust storm. So the question is this dust sourcing from the Great Salt Lake, or is it sourcing from other regional dust sources? So the question is, why would Great Salt Lake be a potential dust emission source? Because since 1985, lake levels have been decreasing, exposing hundreds of new miles of square lake bed. So if we see in this image, you can see where the shoreline is, and in this image, you can see that the shoreline has greatly dropped, exposing all these massive areas of dry lake bed. And this dry lake bed has high concentrations of heavy metals, salts, and toxic elements because of the pollutant quality of the Great Salt Lake. So the question is, does the Great Salt Lake have the potential to produce these massive dust storms? There is different factors that play into the lake bed's ability to produce dust storms. A study done by Reynolds says that if the water table is less than 5 meters below the lake level, then what you have happen is you have evaporation occurring that will break up the lake sediments at the top and will also evaporate minerals. These minerals in the broken up lake bed will make it easily erodible by wind sources producing dust storm. However, if the water table is below 5 meters from the lake level surface, then you will not have the broken up and you will not have the evaporates, meaning that it will not be a dust source. For the Great Salt Lake, we expect that the dust emissions, we will have high dust emissions. From this chart by Reynolds also, we put a red box around this chart to show you where we think that the Great Salt Lake will be. Here we have the potentiometric surface, this is the ground surface, and this is the potential for dust emission. So for the dry lake bed of the Great Salt Lake, we expect that the potentiometric surface will be close to the ground level, and so we'll have this capillary fringe zone where evaporation will occur, producing the evaporate minerals. And the fluffy is what they distinguished it. It's kind of a funny word to use, fluffy. But the fluffy is significant because that has higher levels of the evaporate minerals, meaning that there will be higher concentrations of the heavy metals and higher concentrations of the salts, which will be more hazardous for dust production. Another thing that we need to think about for the Great Salt Lake is the Great Salt Lake has high levels of arsenic. In a study done by Reese in 1997, he showed that most lake beds do not produce high levels of arsenic dust because of arsenic solubility. We can see in this graph that as the groundwater level drops, arsenic will go with it and it will precipitate below the surface. However, in high salinity environments, arsenic levels, the arsenic solubility will decrease, and so you'll have arsenic precipitate at near surface or at the surface, and that has a more hazardous effect of producing arsenic dust.
Okay, now on to our sampling area. Now this is our research that we are working on. Currently, we have multiple locations for dust collectors. First location, out here in the severe desert area, we have placed multiple BSNE samplers. And we are collecting the dust from those areas now, and then we will chemically analyze that dust and compare it to the dust that we collect from the Great Salt Lake bed. Those are the two sources of dust, and hopefully we'll be able to find some distinguishing characteristics between the two dust sources. We are also collecting dust samples from these areas along the Wasatch Front. Hopefully, once we chemically analyze those, we will be able to distinguish where the dust is coming from along the Wasatch Front, whether it's coming from the Great Salt Lake area or whether it's coming from the severe desert area. And these are our samplers. These are the BSNE samplers, which we have placed in the deserts to the south and in the Great Salt Lake lake bed. And these are dust buckets, which we have placed on buildings along the Wasatch Front in Logan, Ogden, Salt Lake, and Provo. Okay, so our procedures. Once we collect the dust, we'll wash it with water into these 2 milliliter containers, which we will then heat up to evaporate all of the water, which will leave all of the soluble elements and the dust at the bottom. Once we do that, we'll distribute the dust and remaining small amounts of water into smaller containers, which we can begin to work on. Our first step will be to add hydrogen peroxide, which will burn off all the organic material, which was growing with the dust. Once we finish that step, we will weigh out our sample, and then we will begin multiple acid leaching steps. So acid leaching involves adding an acid to our sample. We will stir it and let it sit for 24 hours, after which we will centrifuge our sample. After centrifuging, we'll take out part of the liquid, and that liquid is what we will use to send off and do chemical analysis on. Once we finish that step, we will decant the supernatant and do the other acid leaching steps. With those acid leaching steps, we hope to find many different results, which Colin will now discuss.
So we don't actually have any results yet, but this is kind of some of the results that we might expect to find. Last year we took some samples from Alta and from the Uinta. Alta is just east of Salt Lake, and the Uintas are in the northeast corner of Utah. So from these two dust samples that we collected last year, we've already done some of these lab procedures with, and this is the results that we got back. So we're going to use this example to kind of show you the methods that we use to be analyzing our future results that we get to characterize Great Salt Lake dust. So from this you can see that we can there's kind of some distinguishing characteristics between the alta dust and the Uinta dust. If we look here, we can see that there's higher levels of magnesium in the alta dust comparative to the Uinta dust, and also with this one right here. However, this is the concentrations on the left if you're wondering, and this is just the elements on the bottom. However, from this we can't really tell much, and there's not very many distinguishing characteristics. So to better distinguish among the samples, what we will do is we'll take the average elemental concentrations from Whitapole and we'll divide that all by the results that we get. This will give us a result like this that is a lot easier to distinguish between the chemical fingerprints of the sample. So here we can see in the lithium there's higher concentrations of lithium than in the alta dust than the Uintas, and I circled a couple other ways that we can do that. Here is the acid leaching steps that Michael was talking about. So we have our first fractionation, which was an acetic acid, and then our second fractionation, which was a nitric acid. We can see that a distinguishing characteristic in the acetic acid step was that we have higher concentrations of calcium and magnesium in the alta dust comparative to the Uinta dust. Well, however, the nitric acid leaching fractionation doesn't really show much chemical distinguishing features, so that isn't going to be useful in this result. So we'll be using these two different techniques to give chemical signatures to emission sources. So in summary, in order to better understand the characteristics of Great Salt Lake dust, we'll sample emission sources and sample the depositional sites along the Wasatch Front. We'll analyze those chemically, and then we'll compare the emission sources to the depositional dust and to better understand the role that the Great Salt Lake dust has on the Wasatch Front. That's all we have today, so thank you for your time.